We want to find the mass of the region that is above this circle, to the left of this plane, and below this flat plane, with a density that's dependent on height. And so first we'll sketch this. Okay, it's here's the plane, x equals 1, this is x, this is y, and this is z. And here's this cylinder that's below z equals 5. This radius is 2, and that is above the plane, and this is x equals 1. And now we're ready to set up the integral. Okay, the mass of our object is the integral over all of the little square boxes or rectangular boxes in our region times their density. And this mass is also the mean density in this region times the volume. So we start by putting in the z limits. Those just go from 0 to 5. It's very straightforward. There's no dependence. So the limits are 0 to 5 right here, but the limits are also 0 to 5 right here. They don't depend on where they are. Our density is z. That integral is dz. And then we need to identify what the shadow region is, which we've labeled r, and choose a coordinate system, either polar or rectangular, to do the second part of the integral. We'll go ahead and use polar for that. So it was the integral from 0 to 5 of z dz, and theta is going in all directions. No matter which direction we draw our little r line, we want to keep it in. So that's going to be the integral from 0 to 2 pi d theta. And now we have to deal with the r bound. For the r bound, we're going from 0 out to 2 along a lot of these lines in theta. In fact, for all theta that are above this angle and below this angle, we're going from 0 out to 2. So we need to figure out what those angles are, and then for that range of angles, our bounds will be 0 to 2. So we were wrong about wanting a 0 to 2 pi here. We actually need two different sets of r, one that goes from 0 to 2 and the other that does something that's theta dependent in this region. I'm using a triangle to find out what those points are. I know that our radius is 2 and that the x-coordinate is a 1, and so 4 minus 1 gives us 3. This is square root of 3, and that means that the corresponding angle is, this angle is pi over 3. So for this range of angles, for angles from pi over 3 out to 2 pi minus pi over 3, r is going from 0 all the way out to 2, and z is going from 0 to 5, z dz, dr, d theta, and I forgot an r in there, so there's a little r that goes in there. Okay, so that's one piece of it, and then we need to add in whatever's happening on this triangular region. For this triangular region, which we can think of as ranging, where we can think of theta as going from negative pi over 3 up to pi over 3, at this angle, we're starting at 0, and we're walking outward, and our radius stops all the way out here. At this angle, we walk outward, and our radius stops quite a bit earlier. Where's our radius stopping? Well, the place it's stopping is a function of theta. It's because this line is r equals 1 over cosine theta. So our radius is starting at 0, and we're walking outwards until we hit the line r equals 1 over cosine theta. So this second set of integrals is from negative pi over 3 to pi over 3 of the integral from 0 to 1 over cosine theta of the integral from 0 to 5 z dz r dr d theta. Now we'd like to integrate, so we'll do this integral first, and then we'll figure out the other integral. First, we integrate away the z dependence, which gives us a 1/2 z squared from 5 to 0, and that's 25 over 2. And then we integrate in r, that becomes a 1/2 r squared, and we plug in the 1 over cosine theta, so here's our 1/2, and here's our r squared. And this is secant squared that we're integrating, and luckily, because we've been doing a lot of integrals recently, I happen to recall that this is the derivative of tangent, so 25 over 4 tan theta from negative pi over 3 to pi over 3, and then that's a 1 and a root 3, so this tangent, that's the pi over 3 triangle, so this tangent is root 3 over 1 equals 25 over 4 times root 3 over 1 minus negative root 3 over 1, which is 25 over 2 times the square root of 3. And we still have to do that other integral to get the total mass. This second integral is a bit more straightforward because there's no interesting angle dependence in any of the bounds. And so we'll just go ahead and integrate. We're going to get 25 over 2 from this, and then we're going to get, that's going to be multiplied by 1/2 r squared, which is going to be 4 over 2, and then we're going to just end up multiplying by the total angle, so I'll go ahead and do that. Okay, so I've done the z integral, and that gave us that 25 over 2, and now I'll go ahead and integrate in r. Okay, I've integrated in r. I got 1/2 r squared, which ended up being a 4 over 2, and now I'm ready to integrate in theta. So we're going to get a 25 from these terms times theta from pi over 3 to 5 pi over 3, which is equal to 25 times 5 pi over 3 minus pi over 3 equals 25 times 4 pi over 3. Total mass is equal to 25 times 4 pi over 3 plus our previous computation gave us a 25 root 3 over 2. This is a pretty complicated expression, but that's the total mass of our object.